Recording is rolling. It's Wednesday, August 24th. I have not seen you guys in a few days, so let me do some follow up from last few days, and then get you guys kickstarted on linear motion with a lab. And so one thing is, all right. One of the things we did last week, you guys remember, was trigonometry. You guys remember this page front and back? I did tell you guys back on Friday, if you really wanted to take this home over the weekend and take another look at it before you turned in, you could. So if you haven't turned this in yet, turn this in. I do want to pass this back to you guys by the end of the week. So be fair to your classmates and you and everybody. So it's been pretty soon. You should have that today if you haven't turned it in yet. Most of you guys turned it in already. Some other follow-up from last week. You guys remember back on Friday, we did some dimensional analysis. Right, you guys remember dimensional analysis? And I left you guys off with a challenge problem. You guys remember the challenge problem? How much land area would you need to supply the entire United States energy demand with just solar? Assuming there was no engineering complications of like, how do you store the energy? And that on here. Right, so here, I'll show you guys the solution. I know Steven solved this. Did anybody else solve this? Anybody else solve this? Okay, because I know Steven showed me he got the right answer. And so suppose this is the energy demand. Tera is a prefix means 10 to the power 12. Okay, so it's 10 to the 12 with that number. Okay. Now that's watt hours per year. Now watt is a rate used of energy. Even if you don't know that, you can still use dimensional analysis and still get to the correct answer, regardless of whether you know that or not. Okay. You guys look on a light bulb, so many watts, like 20 watts, 40 watts. Ooh, that's a rate that's using energy. I gave guys, well, how bright is the sun shining? Actually, I gave you guys two numbers for how bright is the sun shining: a maximum flux and an average flux. Which of those numbers do you think you actually use to solve this problem? Maximum or average? Average, because sometimes it's day, sometimes it's night, sometimes it's sunny, sometimes it's cloudy. And this average number sort of encompasses all those situations, right? So we don't care about the max, we care about the average. And I gave you guys one more detail, which is efficiency, solar panel efficiency. Now let's think ahead a little bit because I got the answer covered up here. Okay. Suppose you assume 100% efficiency. All the energy that lands on a solar panel gets up being converted to usable energy. That would be 100% efficiency, right? But realistic solar panels are a little bit over 20% efficient. We'll round it down a little bit to 20%. Right, so going from 100% efficient to 20% solar efficient panels, does that mean you need more panels or fewer panels if they're not as efficient? More panels. You need more panels because they're not as efficient. So you need more panels to cover your energy demand. Right. Now 20% as a decimal, that's called what? 0.20, 0.20. So is the last step to consider efficiency, is the last step going to be to multiply by 0.2 or divide by 0.2? You have to divide by 0.2, right? Because isn't divided by 0.2 the same thing as multiplying by 5? Right. So suppose the answer I'm going to make up something silly. Suppose you need like 100 square meters, right? At 100% efficient. But now if it's only 20% efficient, don't you need more panels? So see, if I multiply by 0.2, I'm saying like I don't need as many panels. No. That didn't make any sense. I need to scroll up, scroll over. I need to divide by that 20%. Actually I need like 5 times as many, right? Okay, so with all that in mind, you can actually solve this with nothing but unit analysis, this dimensional analysis. So start with the energy demand. So you've got Tera's 10 to the 12. Watts per square meter. Again, even if you didn't know what a watt was, I used the solar flux. 400 watts per square meter. See how the watts cancels out? Gives you square meters, which gets me a step closer to the answer because I'm looking for some land area, right? Okay. Swap out meters per kilometers. Do that twice for square kilometers places, square meters. Then you have a couple of time units, hours and years. Ooh, that wants to cancel, doesn't it? Time up here, time down here, hours and years. So you can reconcile those units with this couple of steps. Last step, divide by 20% efficiency, right? And that brings you to blah, 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 this many square kilometers of land area. There you go. So that is the answer to that challenge question. And Steven got that. Anybody else try that? And now you know how to do it. One last piece of follow-up. I know I haven't seen you guys in almost a week now. My other classes, I wanted to give some kind of engaging assignment that didn't get my classes completely off track. So just for the record, so you guys know, I had everybody construct this Geneva drive. You guys think this is used in clocks? Tick tock, to turn continuous motion into incremental motion. You guys think this is used in film projection? You have a roll of film, you need 30 frames per second. You guys see that film projector? It's Geneva Drive right there. So everybody made that out of paper. You guys can skip that. It's not gonna be for you guys, but want something fun to do? Be fun to do. All right, here's what we're doing. Have you guys answer this question? So you guys gonna be rolling Hot Wheels cars down inclines. Okay. Hey, do you think this car has some mass? Do you think you'd be rolling for some distance? We'll call it a displacement. Do you think that there's gonna be some amount of time it's been going for? Do you think it'll have some speed at the end? Okay, and one more thing could be this angle of incline. I've set that ahead of time. You guys can see all these inclines out of a lot of tables to 5 degrees. So everybody's incline is gonna be 5 degrees. Okay. Now, oh, and don't worry about the spawn part. That's just for my AP classes. Okay, so I wonder what is the relationship among all those variables. Now, maybe you remember from past science classes, ideally, if you can, in an experiment, you want to change how many variables at a time? One. And that's called a what kind of variable? Independent variable, okay? And then you want one variable to respond to that, ideally, and that's called the what variable? The dependent variable, right? Got independent, dependent, okay? And then everything else you want to do what? Leave the same, and the term for that is called control, right? You want to control all the other variables. We've got a ton of variables we're juggling around here. So what we're going to do is just analyze 2 at a time. Okay? The way we're going to do that is we're going to actually have 4 different experiments running. Do you guys see a card on your desk? There should be from last class. Who does not see a playing card on the desk? Who does not see a playing card? Okay, so it's a playing card. You guys either have a spade, a diamond, a heart, or a clubs. You guys see that? You guys have one of those? Right. Now, depending on which card you have, that tells you which experiment you are doing. So here, you guys have some paper out. So whichever card you have, start copying down that table, which is going to correspond to the experiment you're doing. And I will tell you what it is that you are testing. If you don't have any paper, you guys see got a stack of paper right here, but right next to the checkout laptop. Okay, if you need paper, there's some paper. So you guys copy down the table. Let me start with the spades. A couple of groups have the spade. If you have that, you're testing how does the mass of the car affect how much time it takes to get down the incline. I know, obviously everybody has their angle control, but you guys will also control the rolling distance. You'll do the same distance over and over. So for example, here, got trials. The trials number it like trial 1, trial 2, trial 3. Now I ran out of space here, but try to have at least 5 different data points. Right? It's because tomorrow we're going to put all these data points on a graph. We're going to look for trend lines, curves of best fit. Right. So 3 is not quite enough. Have at least 5. If you have more, if you have 6 or 7, it's even better. Right. Leave the distance the same all the way down. For example, it could be 200 centimeters, 200 centimeters, 200 centimeters. That would be controlled, like a control variable for mass versus time. Okay? Now the mass of the car, you'll change. I do have a triple beam balance back there. I have a digital scale, but if you can't get your hands on those, one empty Hot Wheels car is about 30 grams or so. Then there are some lab weights and some masking tape. You can tape. Do you guys think you can tape some of these lab weights onto a Hot Wheels car with the masking tape? Right? Is the masking tape? Should the masking tape touch the wheels of the car? No, because that'll slow it down. Too much friction, too much variable. Right? You might do like 30, 130, 230. I'm just making up example numbers. That could be sort of like the independent variable. Right? Then last 2 columns here say time and average time. Here's what I want you guys to do. Because the stopwatch, this is like the biggest error that involves it, like most labs, trying to figure out when to start and stop. So the stopwatch. Somebody lets go of the car, the other student trying to use the stopwatch. You guys brought your cell phones today, right? Ooh, good. I was hoping you would, because that's how you guys are going to measure time. Do 3 and take an average. That's what we're gonna do. So you're gonna divvy this up. Do like 1, 2, 3, take an average. 1, 2, 3, take an average. 1, 2, 3, take an average. You guys can do that, right? Do 3 trials, 3 and an average, right? Any questions so far? Right. Now that's only if you have the spades, right? Now everybody else, does anybody else besides the spades need the masking tape or the lab weights? No, because everybody else is going to control the mass of the car, which means you can use everybody else, the diamonds, the hearts, the clubs. You guys use the blank car every time. Just call it 30 grams, or if you want to measure it, you can measure it. You might get like 32 grams or something. Okay. Diamonds. What are you guys doing? X versus T. So what you guys are going to do is vary the location of the car, right? Different, let it go different rolling distances. Okay, like that. And in time, how long does that take? So different trials, use the same math over and over. So it could be like 30 grams over and over. Right? You're gonna do different rolling distances, and you're gonna take time how long does it take. Are you guys going to also do 3 times to take an average? Yeah. So do like 1, 2, 3, take an average. 1, 2, 3, take an average. 1, 2, 3, take an average. You guys can do that, right? Right. Now, you guys, the diamond, I did throw in one more column. I said to square the time, the average time. So, for example, if you get 2 seconds, 2 squared is 4. If you get 3 seconds, 3 squared is 9. Right. That's probably not going to make sense right now, but that'll make sense tomorrow when we're putting the graph together. Okay. Guys good? If you have the hearts, V versus T. Ooh, you guys get to use these speed sensors. Actually, anybody can use the speed sensors, but if you have the hearts or the clubs for that matter, you need this tool to complete your data, right? You guys see I drew the speed sensor right here, to the bottom of the incline, right? So let the car roll some distance and then you grab the speed. Here, let me show you guys how this works. It's got a couple of sensors on it. If I start this thing, it has a unit that says meters per second. Right now it says 0 meters per second. But watch this, a car rolls through, 1.34 meters per second. Ah, that could be a speed, couldn't it? And the symbol for that is lowercase v, like velocity, magnitude of velocity, speed. Let's try that again. Clear this out. Start. So back to 0 meters per second. 2.7 meters per second. Oh yeah. Think this is fun to use? Oh yeah, this whole lab is fun. Yeah, it's gonna be a fun day. So anybody can get their hands on those, but if you have the hearts and the clubs, you have to use that to get this speed. Okay. Mass is controlled. Okay. Actually, the hearts and the clubs is a very similar setup, but you're measuring a little bit different thing. If you have the hearts, you're going to time how much time does it take to roll down the incline. And now you choose different starting positions, but you don't really care about the distance. You care about the time, even though it will be different locations. Okay. If you have the clubs, you don't need a stopwatch at all. Notice there's no time column on the clubs, and you're directly looking, see like what's the rolling distance to get to the speed gate down here. Okay. All right. So yeah. So the hearts and clubs very similar setup. But the hearts are measuring time. The clubs are measuring displacements. Okay. Who has any question? Anything so far? Any question? Okay, guys doing all right? All right. So we just gonna stop this recording. Stop recording.